So it looks like I'm going to have to pick up here on this new video, a new clip. But so here again is the applet that I've posted. I guess before anything else, let me mention that I've turned off these rays, so it'll when you boot up the applet, it will actually have these turned on by default. This is for something called ray tracing, and you will find it heavily featured in the textbook. I tend to kind of lean away from it. Now, ray tracing is really fun, and I think that's why students like it. But it does have a couple problems. Now, the way that it works is you cherry pick a couple rays, which have these special names that are coming from the object. But what happens is that sometimes, for some random reason that may not be clear to you, you kind of have to throw away one of the rays. One of the rays doesn't work. And so basically you're doing it, if you really want to use it for anything, it's because you already know the answer, and so you just throw the ray away because you don't need it anymore. And the other problem with it is that it works really well for lenses, which are coming up, but for mirrors you actually have to have a scale drawing, so you have to actually get a nice scale drawing, and if you don't, then your answers kind of come out wonky. So anyways, I'm not going to use it, so I'm just going to turn them off. Also, this applet comes booted up with the concave mirror as the default when you turn it on, so you're going to have to click over to the convex. So let's see what I do. I can change the object height, so I'm going to bump it up to the maximum height. And the radius of curvature, you can mess around with that, but let's leave it like this because that seems as good as anything. And here is my object distance. So if you go back over to the results that we were just discussing, if you take the object very far away, this is unfortunately as far as I can take it, but if I could take this to infinity, then the image would be at the focus and the magnification would be 0. So that is the result right here. So if the object is in infinity, the magnification is 0, and the image is at the focus, right there. So let me start dragging it in. I'll decrease the object distance. By the way, notice for this, all of the results that it's giving here are basically what are yielded from the equations. So right here you can kind of just make yourself up some practice problems if really what you want to do is practice the equations. The plug and chug on that equation is not hard. If I click over here, you have your magnification is minus di over do. You have your 1 over do plus 1 over di equals 1 over f. So pretty much if you can remember that your focal length is negative and your di is always going to come out negative, and your do is always positive, that's generally true in this particular type. I should clarify, in this particular type of mirror, f is always negative and the di is therefore negative. So I'm not so worried about the plug and chug. I just want you to remember the kind of the overarching picture, which is that if you bring the object in, so if the object is at infinity, the image is at the focus and its magnification is 0. You can see here I've brought the object in a little bit, so the image is still very small, but it's there and it has moved in from the focus. And if I slide this in, you'll see they're about to meet. Now notice that the image is always closer, and because it's always closer, it's always smaller. So again, remember that this equation implies that since the image distance is smaller, the magnification is less than 1. I guess I can also mention, you might be wondering about this minus sign. Well, remember di itself is negative in this case, so the negative times a negative does give me a positive, so the magnification is positive. So the di being negative does imply that the magnification is positive. So we have that the object is moving in toward the mirror and the image is moving from the focus toward the mirror as well, and we get here and just can't quite get there with this applet, but you can see this is merging on plane mirror behavior. So here's the object, the image grows, and eventually if I could put this object right up against the mirror, the image would just be there as well, and it would approach the same size. So we converge on plane mirror behavior as DO goes to 0, DI goes to 0, and the magnification merges on +1. Now, if you can understand that and kind of get the gist of a convex spherical mirror, you've already understood the diverging lens. The diverging lens is exactly the same thing, except for the light passes through because it's a lens, and instead of bouncing off because it's a mirror. So let's take a look at that. So a diverging lens is basically any lens which is thinner in the middle than on the edges. So which one of these particular lenses would be diverging lenses? Any of them that are thinner in the middle than on the edge. These guys. Not these guys. They are thicker in the middle than on the edges. In fact, these are called converging lenses, which we'll take a look at next, and they're a little bit more complicated. So let's try to figure out, let's pick one of these diverging lenses. This is the one that's most commonly drawn. Let's try to figure out how it affects light. This is just a piece of glass or plastic or whatever. It's something that just has an index of refraction that's higher than the air around it, and it's in this particular shape, and what it tends to do to light is highly suggested by the name. So let's take this guy, we'll drop in a optic axis, and the very first thing we usually want to do is we want to check out what will this do to light that's coming from an object that's very far away. So here are our parallel beams, and now we want to figure out how is this piece of material going to treat that. So let's take a zoomed in view of how the refraction is going to work here, and convince yourself that light bending toward the normal on the way in to the lens, so it goes from air to the lens, so it bends toward the normal, that will be up, and then on the way back out, from the lens back out in the air, it'll bend away from the normal, and that will also be up. So convince yourself that because of the shape of the lens, the light gets deflected upward, like so. And similarly for the light that comes in the bottom, convince yourself that it gets deflected downward by getting bent toward the normal, then away from the normal. Both of those will end up with the light being deflected down, like so. And convince yourself that for the light beam that comes to the middle, it will come in at 0 degrees to the normal, so it won't get bent, and it'll go out at 0 degrees to the normal, so that one will just go straight through. So the action of this lens is to scatter the light, which, remember, that's exactly what the convex mirror did. It scattered the light. It took parallel light and scattered it. So for an observer over on this side, these light beams would appear to emanate from a point right here. So that's where the image will be. And we again give a special name to that point. It's the point that light will appear to emanate from if it's actually coming from infinity, and that, once again, is called the focus. If the image was over here on the same side as the outgoing light, remember the outgoing light now, it's passing through because it's a lens. If the image was over here, we'd give it a positive image distance, but it's not. So once again, we have that the image is over here on the opposite side as the outgoing light. And you see the reason why the outgoing light is really nice to tie it together is that therefore we can treat mirrors and lenses on the same footing. So if the light bounces off, well, the outgoing light is over here, but now since the light passes through, any images that are over here would be plus, but again, they're not over here, they're over here. They're on the other side. Now the only thing that happens when you move the object closer, so as I move the object in more, the rays are going to be looking like this. So they're more divergent to begin with, and so they're going to be scattered even more by the lens. Let me take out the parallel light here so we can see it here. And so these outgoing rays now, since they were already diverging when they even came in, they get scattered even more by the lens, and what you're going to see is that these outgoing beams are going to trace back to a point that's even closer to the focus. So the image is now not at the focus anymore. It's moved in from the focus toward the mirror. So as the object moves in toward the lens, as the object moves into the lens, the image moves into the lens. And where does it end? Well, eventually the object and image merge here. So instead of having plane mirror behavior, what you have is pane of glass behavior. So basically, if you're an observer looking through at something through the very central part of this, then the curvature of the lens doesn't matter anymore. The object and image are going to be in the same place. So that's the pane of glass behavior that you have to merge on. So basically, any mirror, if you get close enough, turns into a plane mirror behavior, and any lens, if you get close enough, merges on the pane of glass behavior. So if I go over here to the applet, again, I've turned off the rays from the ray tracing. I have set this to the, I really wish to set converging and diverging. This is really annoying because if you call them convex and concave, it's flipped from the analogous mirror. So just pretend this says converging and diverging. Click over the diverging. And so here what you see is, here's the object. I can't get it far away, but this is as far as I can get it. So this is small. It's close to the focus here. And as I bring the object in, the image starts to grow, it starts to move in, and eventually it should merge with pane of glass behavior. Again, I can't quite do it because this applet won't let me, but these guys eventually merge. So if you're an observer over here, you'll see them basically at that point you start to really see the object where it truly is. Now, if you haven't already picked up on it, there is an exact analogy. If you understand this, you understand this. The only difference is this, that because here the light reflects, this out here is the outgoing side. So all the action happens over here, so the image moves in from the focus. And for this is the outgoing side, and all the action happens over here, which is the opposite side. So really all you have to do is take all the stuff that happens over here and copy it over here, and suddenly you have this. They're exactly the same. I can't emphasize that enough. The only difference is that here the light bounces off, so this is the outgoing side. Over here the light passes through, so this is the outgoing side. And so you're just flipping which one's the outgoing side, and since all the action happens on the other side as the outgoing light, over here it's this side, over here it's this side. Now you may notice that there is another focal length here, but this focal length has no bearing for us right now. It's all about this focal length. The only reason this is marked is because if you did send the light in from the other side, of course everything would be just reversed here, because you can send the light in from either side and the lens will act the same. Same cannot be said over here, of course, because over here, well, first of all, this is not a mirror. The shiny part's over here. And secondly, you can see that this is, of course, a different shape. Whereas over here, it's still thinner in the middle, regardless if you send light this way or this way. So, as kind of a master summary of the convex spherical mirror and the diverging lens, what do you get? You get that the magnification is always positive, the IO is always negative, it's an upright image, it's always in the same orientation as the object, it is virtual, there is no light that actually emanates from the image point, it just looks like it does. The object distance, as it goes from plus infinity to 0, you will have that the image will move from the focus, the focal length, to 0. The magnification will go from 0 to plus 1. So the magnification is always less than 1, or at best equal to it, for this type of mirror or this type of lens. Common examples where you might see this, this kind of mirror, you might see this like a Christmas ornament has this kind of face. If you see those kind of shiny things that they install up in the corner of the ceiling at convenience stores, that's basically the hidden camera. They have one of these domes over it like this, so you'll always see yourself upright and smaller, and that's about it. This kind of light always scatters, this kind of thing always scatters light.